Thank you so much, everyone, for coming, and welcome everyone to Science Society, and of course, um, a special welcome to you, Dr. Yang Bei. And so that the audience gets to know you a little bit, I'll give a short introduction, and then I'll hand it over to Victoria, who usually um, does the rest of the introduction in an interview kind of setting, if that's okay.
Okay.
Perfect. So, Dr. Bai, he's a professor in the Department of Physics at the University of Wisconsin-Madison, where he's a theoretical particle physicist. And he did his bachelor in science at the University of Science and Technology in China, and then his PhD at Yale University. And then he worked in 2007 at the Fermilab National Accelerator Laboratory, and at the CLAC Slack National Accelerator Laboratory, and then starting in 2012, he then started working at the University of Wisconsin-Madison, Wisconsin-Madison, and where he is now a full professor since 2021. And his research interests are theoretical particle physics and physics beyond the standard model, dark matter, and collider physics, cosmic rays, black hole, and early universe physics. And that's all sounds very exciting to me, all those fields. So I'm really looking forward to this talk and this discussion, also the interview. So I'll hand it over to Victoria, and thank you again.
Thank you, Katarina. Yes, we are so excited to welcome you here. And this topic. It feels like you've got a mystery reveal waiting for us. I would imagine everybody agrees. And so my question to you is just to get a bit of background information. Can you think back in your life through childhood or anywhere that you feel that you sensed a particular connection to science? Maybe there is a spark that you sensed from something somebody shared with you, a parent or teacher or anyone in your life, or maybe just an event.
Yeah, I think I think probably I can remember, which is like a Hawking. Hawking has a very popular book about a history of the time, history of time, and that kind of motivated me a lot about pursuing science in general. But in general, when I was a child and also like middle school, high school, I pretty good at math, and so at that time, I'm not sure whether I should pursue math or physics. It's not clear. But I think somehow around the high school, I kind of very into science, and also kind of determined to do science after for as a career, basically. Um, yeah, that history of time by Hawking. I think that's probably the more fascinating book to attract me to keep physics in mind as always. And even nowadays, I think I also probably will ask my daughters to read that book as well. So that's pretty much how yeah, one motivation I can remember. Yeah.
That's really a wonderful answer. Also, because I can imagine maybe one day somebody asking your daughters the same question. And then they could look back, well, the encouragement from my father and these books. It is an incredible book. So can you, yeah, I'm happy for you that you had the choice, that you that you were favoring physics and that you could follow that path, since that was, you said that was what you did favor.
Right.
And yeah, so can you share with us how you came to be working on the project that you're going to share with us today?
Oh, yes. So this specific topic I'm talking about today is a little bit on the speculation type direction. But in general, I'm working on trying to understand what is the identity of dark matter in general, and then working on some specific very very heavy, very very large size dark matter model. And then if you get into very extreme limit, then the dark matter could be very very heavy, could be could be planet mass or even like a star mass. Even before this project, I already have like probably a few projects along this general direction. And then we thought, even though may not be high possibility, but we thought like maybe we should not take it as granted to think about all the discovered or detected exoplanets are made of ordinary planets or ordinary matter. Maybe there are some possibility some exoplanets they may be made of dark matter. Especially we in the last few years we are studying some other dark matter models. We know that some models they could have dark matter state to be very very heavy and very very sizable, and so that's kind of the very in some sense it's very natural for us to think about perform this study actually. Yeah, but on the other hand, I also want to even say that at the beginning is very speculated, and so probably the probability for the current like Earth size or Jupiter size exoplanets, they are made of dark matter is not very high. But still, we want to check this possibility to know whether it's true or not.
So it sounds like it just made sense. And here you are, in the scheme of the universe, showing up right here, right now, with your interests and your background. And so it's your turn to work on this
Yeah,
subject.
yeah.
Yeah, and reveal it to us. So, okay, well, thank you. And
Mm.
at this point, I will just say the mic is yours, and we're here to help with questions that friends may put in the chat. We can share those with you, and then if it's okay with you to have a Q&A following your talk, then we can bring guests, friends up as well to do that. So otherwise, the
Yes.
mic is yours. Thank you.
Okay. Just one question. So, how do I go through the slides? Should I just say that the slides page number one, or
Yeah,
I don't know.
exactly.
Okay,
Yeah,
get
yeah,
it.
yeah.
So because everyone will open the PDF, or will open the PDF file. Okay, I get it. Okay, cool. Okay, so yeah, let's start with page number. Yeah, basically the first page, right? So just thanks for the invitation. So I'm very happy to talk about dark exoplanets as the topic, and also some recent paper on archive. So the second page, which is my collaborators, and one is my student, one is my postdoc worked with me before, and we have been keep thinking about the mysteries behind the dark matter. And there is an archive number. You can check, and if you want to read more about the paper, and as well as some references, which is some references maybe a little bit useful, and depends on your background. And um, so okay, but for this talk, I will try to make it a little bit more pedagogical, and trying to probably not just only talk about the exoplanet, but just give you a general sense how we think about the mysteries behind the dark matter. Okay, page 3. So as what I said, probably I first give everyone a little bit more general physics. A few slides about general physics. First is like a matter, right? Because I was main research direction is about dark matter. So we first trying to understand the ordinary matter. So just in case you forgot that the ordinary matter is made of atoms, atoms is made of nucleus, nucleus is made of protons and neutrons. And if you look at the inside of the protons, they are made of quarks and gluon. But however, in nature, we don't have a free quarks. The quarks and gluons, they are always stay inside the proton. And sometimes if you heard of the word, and we know that there is some kind of a confining, in a sense, what is the force to combine quarks together? That is so-called strong dynamics or quantum chromodynamics. So that is the force to hold them together such that there is no free quark can come out of a proton. And so they just stuck there and forever. Okay, so other than matter, so now let's get into page 4. We also have some interactions or some forces for those matters interact with each other. So so far we observed the forces. There are 4 kinds of forces in nature. So one is electromagnetic force. That's well known because the light and the sunshine, all kinds of things, cable, and that is related to the electromagnetic force. And another force, which is gravitational force, which everybody feel. So that's the planet or specifically the Earth moving around the sun. So that is the gravitational force. I also explain, maybe get into more about the gravitational force, which is a little bit more relevant for today's talk. And but there are other 2 forces. They are not probably not familiar with for you guys. One is so-called weak force, which is trying to describe sometimes we call it a beta decay, some radioactive decay. For example, what this symbol is N. N stands for neutron, P stands for proton, E minus stands for electron, and nu E, nu E bar, that means that is anti-neutrino. So basically, this is trying to describe the neutron decay to proton plus electron. Sometimes electron we call it a beta particle, and the anti-neutrino. So that kind of interaction, how the neutron decay is described by weak force. So the last one, which is a so-called strong force, which I was mentioning in the previous slide, which is the force to hold the quarks together inside a proton. And this force I will also come back, which I will kind of use this force as one possible analog force in the dark matter sector. And to think about that, maybe the dark matter sector has a similar story. So just trying to remind you that there are 4 observed forces in nature, and there are lots of fascinating questions about all those forces. For example, even the electromagnetic force, weak force, and a strong force, at a very high temperature or high scale, they could become a one common force. That's why we are called by the unified theory to group those 3 forces together. And also it's possible like all those 4 forces, they could become a single one if there is a quantum gravity theory and with the string theory to be the most popular quantum gravity theory behind that. So there are lots of interesting fundamental things theoretical physicists they are trying to understand and behind those forces. Okay, but let's continue into the page 5. So this is what we know about how to describe the visible universe to some extent, the so-called particles of the standard model. And so there are some, for example, the upper one, like a U, C, T, D, S, B, there's just some quarks. So U stands for up quark, C stands for charm quark, T stands for top quark, D stands for down quark, and S stands for strange quark, B stands for beauty or bottom quark. So you can see that there are 6 kinds of quarks, and on the lower green color, that is leptons. Then you have electron, which is ordinary life. We know that. But then there is a heavy lepton or heavy electron. If you think about it, there is muon and the tau, as well as three kinds of neutrino. Then there is on the blue color, that is a gauge boson. We have a photon, which is trying to describe electromagnetic interaction. Then we have a little g that stands for gluon, which is the strong force mediator. Then there is W and Z, they are mediator of the weak force. In the center, we have this little bit more famous Higgs boson. And if you pay attention to the news, probably you already noticed that around 10 years ago, 2012, the Higgs boson get discovered. As a result, we have a little bit complete story for this so-called standard model, and to describe the visible matter. And okay, so continue. Now let's get to next page, page 6. Let me mention a little bit more about this gravitational interaction, which is probably even simpler without like a general relativity. We just talk about like Newton's law, for example. So this one probably it's easy to describe using a little bit of formula, but I will promise like I will not show too many formulas in this talk. So you can think about it, there is a two-body system trying to understand the gravitational interaction. The first one is you can have some planet moving around the sun in the middle, for example, right? So to describe that, then there is some rotating velocity of the planet around the sun. And we could use the quote centrifugal force, which is on the left side, mv squared over r, equals to the gravitational force, which is g times little m, capital M. Little m is the planet mass, the capital M is the star mass, divided by r squared, which is the distance of the planet to the star. This g is a Newton constant. Using this simple equation, you can derive what is the velocity, which is the square root of g times m over square root of r. So it just tells you that if you fix the center mass, then you anticipate the velocity is going down when you increase the distance between the planet and the sun, under the star, for example. So what does this mean? That means you think about our solar system, right? So you say, oh, there's some Jupiter, there is Earth, then basically Jupiter is farther away from the sun, so that means its rotating velocity will be smaller compared to the Earth's rotating velocity. Right? But one interesting thing is you when you if you pretend that you don't see the middle star, right? Suppose the star for some reason you didn't see that, for example, in the nighttime, right? Suppose you don't see the star, but you still have the Earth rotating around the sun. So basically, the physics law should be independent of whether you can see by the center mass is there or not. You even though you cannot suppose the star does not emit a photon, but still it provide a gravitational potential or gravitational force. The planet still will move around the star, the center mass. So that means we get into the next slide, page 7. So in principle, we can let me change a little bit the story. We can go to a little bit larger size. We can think about a galaxy, and so then in the galaxy we have like a 10 billion, 100 billion stars, and you can observe those stars. You can measure its velocity, in a sense, their velocity around the galactic center. That velocity you potentially can say, oh, depends on the different location of the star from the center. Then you can collecting a bunch of data about this rotating curves, for example, or in some sense the velocity of those stars as a function of the distance to the center. So like what we mentioned previously, right? Newton dynamics, you Kepler law, for example, you anticipate the velocity is 1 over square root of r. And okay, So next slide, and now you can, which is page 8. Now you can see that oh, I collecting data. So I can measure one galaxy. This is specific some nearby galaxy M33. You can observe what is the velocity of those stars around the center of the galaxy, and you collecting data, which is the which is the yellow dotted points. So then you realize that somehow the velocity as a function of r, capital R, right? Previously we say that if it's all the mass is concentrated in the center, we should anticipate the velocity decreases as you go far away from the center, right? Which you anticipate going down. So basically, if you think about, I only see the visible mass, or all the mass is coming from visible light, for example, then you should anticipate to see this kind of dashed line, and at a little bit far away from the center of the galaxy, you should anticipate the velocity going down. But I actually observed the one which is the solid line from the feet, and also those data points, right? But you can see that you don't see the velocity decreases as a function for capital R away from the visible center. So in some sense, that give earlier evidence that some galaxy there are some missing matter. Those missing matter, they're not visible. What we mean visible means they don't emit light, and so there are different kinds of matter, right? And so that's why early time people measure this, they could discover the existence of dark matter. So go to next page, page 9, and so that's just trying to demonstrate that the situation is not just one galaxy, but there are many other galaxies. Probably now we have I don't know, maybe more than 100 galaxy rotation curves when people can reconstruct to show the similar behavior, to give you the evidence that there are dark matter in existence in galaxy. And this is, for example, some earlier curves by Sophie and Ruby, and to measure the rotation curves. Okay, next slide, page 10. In principle, there should be more evidence about the existence of dark matter. So here I just show another way to know the existence of dark matter, which is so-called gravitational lensing. So what on this plot is, so first you have a telescope, which is on the left lower corner, which is the Earth, right? So that's a telescope. And you have some galaxy on the other side, which you can think about that is a source. And in between, there is potentially some other galaxies, for example, and they both almost like a lens. And so what's going on here is there are light coming from the background source, and the light, because the light carry energy, and so this requires a little bit of general relativity. So the light will be bent by the gravitational well of the lens. As a result, you will see multiple images on your screen. If you think about that source has some screen, you will see multiple image, and then by like unfold this kind of image properties, then you can infer uh, how much matter in the lens, and you can also use that to measure how much dark matter existence in between the source and the telescope. So this is another gravitational lensing way. And later on, we will talk about like exoplanet. Indeed, the gravitational lensing is one of the method to detect exoplanet. Okay, so continue. And there are another evidence. I think there are tons of evidence nowadays about the existence of dark matter. And this one is like the image after the like bullet cluster collision. So you can basically think about that there are two clusters, galaxy clusters. This is image after they meet, passing through each other, and then you can see that there are two kinds of colors. One is the red color, one is the blue color. Blue color you can using similar to that gravitational lens is the total mass, because the mass will source gravity well that can bend light. So that is the total, the majority of the mass of those two systems. And the red color is the so-called X-ray part, and that is the mainly the visible matter sets. And this image is a little bit more dynamic to specifically show that you do have two kinds of matter for those two galaxy clusters, and the dark matter is mainly hung around this blue color region, and the ordinary matter around the red color region. So you have a little bit more visualized ways to see the existence of dark matter. Okay, so but there are other ways. For example, there is a Planck satellite. They are measuring the so-called cosmic microwave background, and by looking at those same so-called SMB, and look at the data map, and to analyze the correlation from one region of the sky to another region of the sky, we can also quantitatively measure the so-called energy budget of our universe, which is probably in some sense the bigger picture about our universe, what's going on. So there is most of the energy in our universe is so-called dark energy, and dark energy also related to the cosmological constant, which is in the current universe, which is help the universe accelerate the expansion. But there are other two parts which you can say that dark matter occupy maybe the even larger fraction than ordinary matter. And so if we just look at the matter pie of our universe, since we leave aside of dark energy, so that's another very mysterious part, and physicists are still study the property of the dark energy. But suppose we just look at the matter pie of our universe, you can see that the dark matter will occupy bigger fraction than ordinary matter. The ratio maybe is around 5 point something, and around 5, that ratio. So basically we have more dark matter in the current universe than ordinary matter. So that's, in some sense, that's the one of the biggest research direction I'm kind of conducting, is trying to understand what is behind the dark matter. So why is that? Because if you go to next page, should be page 14 now. And so for the ordinary matter, like what we were talking about at the beginning, there are 4 forces. There is a Standard model. There is all kinds of particles: quarks, lepton, the gauge boson, photon, the gluon, W and the Z gauge boson, for example, Standard model Higgs boson. But at this moment, we don't have a kind of what I say, like we don't have any confirmed explanation what is behind the dark matter part. And so dark matter could be as complicated as the visible part, which is the Standard model. It could be maybe contain many particles, maybe contain also different kinds of forces, maybe has its own dark electromagnetism, or dark QCD, for example. And another thing is, like, we also don't know how the dark matter sector interacting with our visible sector or our Standard model particles, for example. Except that we know that dark matter, they are matter, so they have a gravitational interaction with Standard model particles. So that's pretty much the only thing we know about dark matter. And we also know that they don't carry electromagnetic charge, and otherwise it's much easier to notice their existence. So they are a little bit dark, means they may not carry sizable interactions under electromagnetic force, weak force, and strong, our Standard model strong force. So that's a big mystery. Okay, so along that mystery, if we go to the next page 15. So then I don't know how long, probably we have like over 50 years of after astrophysicists or astronomer uses a rotation curve to demonstrate the existence of a dark matter, and maybe more than 40 years, 50 years, we have a thinking about what is the underlying model behind the dark matter, but we don't have a clue. So here I just give you a sense what is a little bit incomplete list. So because there are so many theoretical models behind or as a candidate to explain dark matter. So if we go to the heavy side, we could have this BPH that stands for primordial black hole. So like you probably noticed that in the last few years, there is a LIGO merger of a black hole merger, right? So but that is like astrophysical black hole. So we have two types of black hole. One is astrophysical black hole, one is maybe the primordial black hole. So primordial black hole, earlier time, like people thought that may be a possible dark matter candidate, but now it's there's still some possibility, but people are still working on that direction. And another one, which is a so-called dark quark nugget, which I will mention a little bit more detail, use that as an example. And then there are some other things, various of new type of stars. This one is like called Axion star, and just some other specific particles. They maybe can get heavy and form some star. And but if we lower the mass, so here what I'm plotting is the log 10 of the dark matter mass over EV. So this is a little bit a non-trivial unit in particle physics. We use EV, GeV. Maybe I give you a little bit of orientation. So there is a M Planck, which is a Planck mass scale. The Planck mass scale, I think it's around 10 to minus 4 gram. Basically, this number 20, that is 10 to minus 4 gram. So that's like a routine life sets around that mass. Okay, but then you can below the Planck mass, you have sometimes called a WIMP, weakly interacting massive particle. Then there is ADM. ADM stands for like a asymmetric dark matter model, which is predicted that the dark matter mass could be around like a proton mass or neutron mass. And below that, then there is a little bit more called Axion, which is another very little bit lighter and um, rough, like a 10 to minus 11, 10 orders magnitude or 11 orders magnitude lower than the electron mass, for example. And even lower than that, there are some called fuzzy dark matter, and there are many names you probably never heard about. But I just give you a taste of what theorists are kind of proposing. So some models, they have various of different motivations for why we are thinking there are some non-zero possibility. Maybe dark matter has mass like that. Okay, so let me continue. Go to the next page, which is page 16. So one specific dark matter models I want to talk about is a microscopic dark matter model. The motivation is following. When we look at the ordinary matter, right, in our routine life, so I mean there are all kinds of matters, but we obviously we don't say electron by directly. We don't say quarks directly. We don't say proton directly. Right. We basically say routine life. We just say some bigger ordinary like microscopic object basically. So think about it in that way. One way what I kind of motivates myself to think about dark matter is like maybe the first impression or the first way we detect the dark matter is also like its microscopic property. So what I mean is like which is like the slide of page 17, is maybe dark matter is also can be even though there may be some underlying dynamics or some underlying constituents, but maybe the first impression we can say or even detect the dark matter is they are in some composite state, and which we can call just in this talk call it microscopic dark matter, for example. So maybe we can first say like dark table, for example, and as a first impression, we detect the dark matter. Um, so here I just want to say that indeed there are some models, and we can study. We could have the dark matter state. Since the dark matter could be in various possible states, like ordinary matter. So for example, the ordinary matter, you could have some nucleus. If you think about what is the baryon number, right? So the main set in nucleus. But you also can have a free neutron, free proton, for example. And so similarly, maybe energetically, in some classes of models, you could have a dark number mainly setting in some microscopic dark matter state. And so that's one possibility. And so here, go to next slide 18. So here I just a little bit talk about one specific model. I probably a little bit too complicated if you are not study physics. So here, but I still can use the ordinary matter to give you a sense this particular dark quark matter, what it looks like. So ordinary matter, right? We have a nucleon, which is a proton and a neutron, and so that is we can call it that hydron state. So the hydron state, the hydron is in one specific phase of QCD, which we call it confined phase. But even in the ordinary matter or in QCD in our standard model, there could be another type of matter, quark matter, so-called quark matter, which is you could be the QCD could be unconfined in a sense it's in a different phase. It's basically you can think about there is some states they may be in the water phase, some in the ice phase, for example. If I use the water and the ice as one example, and energetically it depends on the external parameters you could face is preferred or one state is preferred versus another state. Right? And, similarly, if I'm thinking about just the analog to the ordinary hadron or ordinary quark and QCD, quantum chromodynamics, I can think about it like maybe there is similar, there is a dark QCD, for example, there is dark quark, and the dark quark they could be also can have two type of states. One state is dark hadron, and one state could be dark quark matter state, for example. All right, this is again, this is a hypothetical theory, but I thought it's very reasonable because our ordinary matter is mainly made of proton, neutron, or nucleus and electron, right? But the main mass of our proton and neutron comes from QCD, come from a strong interaction, basically. So that's why maybe the dark sector is also has a similar dark QCD, for example. So that maybe there is a dark hadron and a dark quark matter, for example. So that's kind of the one kind of extension and one analog ways to think about a dark sector in terms of our existing knowledge of visible matter. Okay, so now get into the next page, page 19. So here is the so-called phase diagram of dark QCD, and obviously we should also have the similar phase diagram for ordinary QCD, right? So what we are plotting here, on the right side, sorry, on the x-axis, horizontal axis, is that so-called chemical potential. Roughly speaking, you can think about that is how dense of the object is, or the number density. And on the y-axis or the vertical axis, that's the temperature. So what are we plotting here? So we are plotting that there could be a phase transition when you lower the temperature, right? When we lower the temperature, water will become ice, right? And similarly here, when you lower the temperature, some high temperature phase, which we can call it a dark quark gluon plasma phase, that can become dark hadronic matter phase. So then there is two type of phase. And there is unconfined phase on the high temperature. There is a confined phase on the low temperature. There may be a phase boundary. There may be first order phase transition to separate the those two type of phases, and so this can happen. Then for given theory or dark QCD dynamics, we can analyze what's the property, what is the orders of the phase transition, and what is the dark quark matter property. And in general, those things can be estimated or calculated, for example. So here, I just trying to say, it depends on specific number of color, which is just depends on specific model parameters. The dark quark matter could be the preferred state for some dark QCD model. Okay. Okay, so this is just what I'm telling you is that in some analog to our strong dynamics QCD sector, there could be some dark QCD sector, and there is a dark quark matter, and there are some maybe phase diagram for the dark quark matter, and when you go to the next page, page 20, then you can think about like our universe at a very high temperature, at a very early universe. The temperature could be very hot, could be very high, and then you can almost think of like a boiling water, and then there is you cool down, then you could have some bubble to be formed, and to describe, for example, the first order phase transition, for example. So go to next. So here I just give you a little bit of sense what will happen. So next page 21. So you maybe have some critical temperature for separate those two type of phases. For temperature very high, and here we use red color. That means that you have the so-called in the dark quark gluon plasma phase. So basically, you think about there are some quarks, there are gluons, they are they are not in the hadron states, so they are just freely moving. Because temperature is very hot, you can think about that proton and neutron, they are melted. But as you lower the temperature, which is next slide, page 22. When the temperature is comparable to this called critical temperature, then the bubble, the hadron bubble, can be formed. Once it's formed, and also it's preferred for that region, and so those bubble will grow, and they grow. So which is this blue color. So the blue color, which means that you can almost think about when you cool down, then there is ice phase. So the ice phase starts to grow, and so that will try to occupy more volume. And go to the next slide, which is slide 23. And those hadron bubbles, they will grow, and eventually they will overlap. And then there's some overlap region and corner. Then that will be the corner. You maybe still have that kind of unconfining phase, which is the red color, to stay there. So now once the blue color occupy majority of the volume, we can turn around, and we can turn around and to think about that. Oh, now the universe is mainly in this confining phase, and but however, those squeezed by those hadron bubble, the small corner of the red color, so they maybe have some quarks constituents to, or dark quarks constituents to be squeezed in a small pocket, and those pocket maybe will be hung around there, and they prefer to be holded there. Then they can balance this kind of a vacuum pressure and by this hadron phase, and they maybe have some degenerate Fermi pressure to balance that, and so therefore they can hang around there, and hang around there. This will be one possible ways we can form this kind of dark quark nuggets, and as one potential microscopic dark matter state. Okay, so this just I just demonstrate one possible ways you can form microscopic dark matter, but obviously there are some other ways which we can form them in the early universe. Okay, next slide, slide 25. So I just give you some parameters of the dark quark nugget mass, which is in the vertical axis, versus some different dark QCD phase transition temperature. So basically, you go to lower temperature, you will generate a bigger, heavier dark quark nuggets. And so here, the vertical axis is in gram, so you could even generate like a 10 to 24 gram, for example. So just to remind you, like the sun is 10 to 33, and so this will be like 10 orders of magnitude lower than solar mass. But after you initially form those dark quark nuggets, in principle, there could be also later evolution as the universe cool down, and the dark quark nuggets maybe they can meet other free dark hadrons. They maybe absorb them. They can grow their mass. So there is still follow-up dynamics potentially can grow the dark quark nuggets to let them become heavier and heavier, for example. And, so then also we did perform some calculation for that. Okay, so now after set that, so here 25, and so basically I give you some possible dark microscopic dark matter model as well as its formation. In general, you could form, and their mass could be can be microscopic mass, like maybe get closer to planet mass, for example. So now obviously now next the question is how do we search for microscopic dark matter model, which is like the slide 26. So the first thing you want to do is you those dark matter, because they are dark, they may not have any other like electromagnetic interaction with visible matter. But however, they are matter, so therefore they can still have the gravitational interaction. So one way is this kind of gravitational lensing, right? So which I already mentioned a little bit when we talk about the dark matter evidence. But what we are showing here, even though you have Earth and you have some star, the telescope on the Earth, and then you have some black here, the so-called object, dark matter object is black hole, but also applied to microscopic dark matter, because the only relevant is the total mass. And so when you have this dark matter object passing in between the star and the telescope, and if their mass is large, then they potentially can make the star brighter. This is the micro lensing effect. So this is, to some extent, this is the best way, more universal way for us to look for microscopic dark matter model. Okay, so like the slide, page 27, which is just there are some experiments, few experiments. They are looking for micro lensing events, and for example, this HSC is a Subaru. There are some Oga and or Eros Macho, and here what we are plotting is the dark microscopic. Here we just use the symbol dark macho, but it's equivalent to the microscopic dark matter model. Different masses, and also the y-axis is different radius. And so the dark quark nuggets I was talking about, so that is the like a crossing lines to give you a guidance. So here just to give you a sense, if those objects they can account for 100% dark matter, then they should be then you already requiring their mass. For example, if it's dark quark nuggets require they are for example above or below certain mass, for example, and so we can use those micro lensing to search for microscopic dark matter. Okay, next slide. Now I get into the real topic, but which is exoplanets now, right? So page 28. So as you can see that people are also looking for the exoplanets. There are many ways to search for exoplanets. So the most popular one, which is the first on the first row and the first panel, which is the so-called transit photometry, which is you have the planet block the starlight, for example. So then you can see that the brightness of the star will have a little bit drop, tiny little bit drop, depends on the radius square of the planet over the radius square of the star. Then you have some relative drop. Usually that drop is tiny, is like a 10 to minus 3 or 10 to even 10 to minus 4 level. So you have a tiny change of the brightness of the star. There are some other things like transit timing variation. Let me ignore that. And on the lower row, you have a radial velocity. Basically, you have the planet moving around the star. The star has a little bit of wobbling, and so that wobbling in the radial direction, which is the direction to the distance to the telescope, And because that distance, radial distance change will change the star light wavelength. This is a so-called Doppler effect. And so you could, in one part, you will see the wavelength is lower, and which is the blue color showing up here. And in the other part, maybe the wavelength will be higher, which is a red color, for example. And so that is one way you. But this radial velocity, you can only measure the exoplanet mass. Then you cannot measure its size, and because this is just pure gravitational effect. Okay, but for the transit photometry, and you can, because you see the image, right? So you know the radius, then you can potentially measure the radius of the exoplanet. And the microlensing, continual microlensing we already mentioned, and you can have a little bit of additional spike um, on the light curve of the star from the microlensing. Then there is astrometry. Astrometry, again, similar to the radial velocity. And, then you can have the location of the star also changing, and doing this kind of star position changing in the sky over time. And as a way, you can notice the existence of there is another planet surrounding or moving around of the star, and changing its position like this specific way. The last one, which is direct imaging, which very simple. You have a starlight and hit the exoplanet and reflect it, and then you just direct the image of that. And this is a page 28. Now go to next page, page 29. So this is probably not updated, but 2019. I just found like this page. It's very easy summary and about the different methods. How many exoplanets you observe. So again, most of the exoplanets, they are observed by this transit light curve method, which is around 3,000 at that time, a few years ago. And then there is a radial velocity, which is sensitive to the exoplanet mass, which is 870. Then some other subdominant observation for using other methods. The astrometry, for example, observed 10 at that time. And but now we may have more with Gaia data, another telescope. There astrometry could have more observations. Okay, so now about the title of this talk, which is next page, page 30. So which we're asking, how do we know that those observed exoplanets, they are ordinary planet, or they are made of dark matter, or which we can call it dark exoplanets, for example, right? So in our paper, we basically trying to think about how we know how what would be the systematic way to notice. So the simplest one, which we can easily check, which is the mass radius relation, because there are some exoplanet you measure its radius as well as its mass. So that's those data points about observed exoplanets on the mass and the radius relation. And you can look at this one. You can see that indeed there are some interesting planet. I mean, this slide probably will help astrophysicists trying to, or even astronomers trying to understand how the planet is formed. Then you can easily see that there are few kinds of band. Then on the lower left corner, that is like a so-called rocky worlds, which is like Earth and Venus sets. And then there are some transition point like Neptune and the Saturn, for example. And then there is a heavier mass, like above like 100 Earth mass, which is Jupiter regime, and there is more population because the united mass is heavier, the radius is large, so it's easier to measure. So there is also some detection bias. So in principle, there could be also maybe more smaller mass, smaller radius exoplanets, but it's just more difficult to be detected, for example. So look at this distribution, right? So this is most of those observed exoplanets in this on this slide. They probably just ordinary planet, and why? Because you probably can have some or using ordinary physics, you potentially can model the exoplanet mass radius relation to explain those this scattering plots, for example. But however, if you do have some other, which I'm plotting in kind of schematic, so if you observe some planet which are on the either left upper corner or the left, sorry, right lower corner, then you very confidently, I think you can say that is a dark exoplanet. Why? Because, for example, in the right lower corner, even you think about the planet is made of iron, which is probably the most dense elements in terms of the visible matter, then you still cannot get into that region. So therefore, observation of any exoplanet with mass heavier, radius smaller, which means it's much more denser than iron, and you have no doubt that will be something something not ordinary matter, and so that could be easily dark matter or some unknown stuff, right? So that's probably the easiest way. And obviously, at the current moment, there is no observed exoplanet populate in that region. So which means we cannot claim there is any dark exoplanet, right? But this is the easiest way, mass radius relation, to give us a hint about the existence of something non-ordinary or extraordinary exoplanet. Okay, next page 31. Another one which is also kind of simple, and which that's why we didn't do any detailed analysis, which is spectroscopy, right? If you think about what exoplanet science in general, the people looking for another human being can live in those exoplanets, right? So one way is they want to know the water, right, existence, H2O, and also with the latest James Webb Space Telescope, and the people can have a little bit more spectroscopy property of the planet as well as its atmosphere. What I'm showing here is some specific atmosphere of the specific exoplanet, and you can see that then you will have a you can match to the ordinary matter or those specific chemistry. What is the absorption line, for example? And so that's where more well predicted and we're also well measured, right? But if it's dark exoplanet, then you probably anticipate that you should have those spectral lines, absorption lines to be missing, or you even have a dramatically different lines, for example, and that would be the easiest way to notice that you have something obviously not ordinary matter, but for some reason it's also same mass as exoplanet. So this is spectroscopy is probably the second easiest way to notice something different from ordinary exoplanet. Go to next page, which is page 32. Another little bit not so immediately obvious, which is so-called missing transit, right? So the missing transit. So what we're plotting here is, if I'm thinking about dark matter, most likely dark matter will not interacting with ordinary matter by photon or by light. So in some sense, most likely the dark, even though there is some dark planet or dark exoplanet, so they probably will be more transparent to light, to starlight. So in sense, if you have the transient, so they will not block the starlight. They will not change the starlight. And however, you have some other methods to study the property of exoplanet. For example, you can have the radial velocity, which I also mentioned, right? So we say which is a planet around the star, and the star is wibbling, and then you changing the frequency of the of wavelengths of the starlight, and as a way to measure. So that will be sensitive to the mass of the exoplanet. And then another, which is astrometry, for example. So they can also give you additional orbiting information. Combining of that, you can give you the orbiting information. If you completely determine the orbiting information of the planet, exoplanet moving around the star, if you know that the orbiting has to have origin, the planet will block the starlight, but then you realize that you don't observe that blocking of the starlight, which we can call it a missing transit. Then you know that exoplanet is also not an ordinary exoplanet, and maybe could be darker planet. So in some sense, the third way would be missing transit. Okay, so probably, in my opinion, this missing transit probably is the most likely, probably the best way to search for the dark exoplanet. But at this moment, we don't have too many. Maybe we have like only a few observations of a few exoplanets. They have both complete determination of this orbiting information, but not yet not clear has that been maybe the exoplanet mass is too small or the radius is too small such that your transient observation has not yet show up, for example. Okay, so the next one, which is page 33, the the last method will be like a transient light curve. In a sense, oh, you have the dark exoplanet. They are not totally transparent to light. They are also not totally opaque to light. So they're totally, so maybe they are sets in between. So which is this probably a little bit coincidence happening. And then you can define some different transmittance for the dark exoplanet and compared to ordinary planet. Then you can define some function. Maybe the ordinary planet, let's just say that you have those blue dotted points. Maybe the dark exoplanet is a little bit block less light compared to the ordinary planet. Then you maybe want to do a little bit more detailed data analysis to distinguish that. And so here, next page, which is 34, we don't need to get into those detailed data analysis. Basically, we just choose the two typical exoplanets to perform a little bit more detailed light curve data analysis to check which hypothesis works better, whether it's ordinary exoplanet or dark exoplanet works better. But for those two exoplanets choosing here, we found like yeah, it's like ordinary exoplanet works better. And the next slide, which is page 35, and which just give a little bit of contour plot about about this kind of dark exoplanet model parameter. One is tau zero, one is RP. RP is just the radius of the exoplanet over the star radius, so define some dimensionless quantity. And in the y-axis, vertical axis is tau zero, which is how much the light will be blocked by the exoplanet. And when you have the ordinary planet, you basically have tau zero to be very large, and this contour basically shows that you basically prefers to have the ordinary exoplanet explanation for those two specific exoplanet light curves. But on the other hand, you also, especially for the right panel, you also cannot 100% exclude some dark exoplanet explanation. Right? But here we just use this two exoplanets as two examples to show that how we should perform the data analysis, how to take into account some other star properties like limb darkening effect, for example. And but in principle, we should analyze a few thousand exoplanet light curves, but that's a little bit um, uh, I probably that requires some long trivial data analysis method to analyze all of them at the same time to see any exoplanet observed light curves, so they can prefer this kind of dark exoplanet explanation. But that's probably wait for future work. Okay, so let me stop here. So let me give you guys a little bit next slide 36, and which is some thing. So basically, mainly I want to say that our physicists, particle physicists, we are still trying to understand the nature of dark matter is fascinating, and one type of dark matter candidate I have been working on, which is this microscopic dark matter, and which really requires some kind of astrophysical methods to detect, and we have some other ways to detect, which the microlensing or exoplanet, this type of methods is just one of them. The current exoplanet maybe can be made of dark matter particles, for example. For some exoplanets, I don't think we can exclude that possibility. even though personally I think this hypothesis of a dark exoplanet probably is not likely. Why? Because uh, if I'm thinking about some independent dark matter sector, I probably will not anticipate, even though they form some microscopic state, I don't think they will be exactly as our ordinary planet mass radius. Probably that's a little bit of a non-trivial coincidence. So because of that, I think the prior is not very high. But still, I feel like as a scientific rigorous, we probably still want to conduct or throw out the searches to check observe the exoplanets, whether they're really ordinary exoplanets or not. Okay, let me stop here. Thank you. Yeah, wait for your questions.
Well, thank you so much for this wonderful presentation and for guiding us through the principles and then going into this really interesting recent work of yours. It was really wonderful to follow along, and thank you so much for taking the time to explain this um, in a way that yeah, we can understand your work better. So we really appreciate it. Thank you. And I know Gilbert, you posted a few questions. Do you want to ask them, or do you prefer for me to read them? Because I don't know, maybe you're in a noisy environment.
Yeah, I don't mind. I can actually ask them.
Mm.
First off, thank you, Doctor, very much for this fascinating topic. Your work is quite impressive. I had
Thank you.
a few questions I wanted to get your say on. My first question is, do you think we can actually attribute dark matter to curvature of space-time? Meaning, you can set up specific massive objects in a certain way where they interact together, affecting a certain region between them, creating an extreme curvature that we might observe as mass, but it simply could be a curvature in space that is causing different objects to move, let's say, in an irradical way, or as if they are moving around a massive object. That's my first question.
Okay, let me answer this question. So actually, the from general relativity, when you have the matter, which is here we're talking about dark matter, and indeed that changes the curvature, changes the space-time around that. So in some sense, the dark matter already doing the specific thing you were asking. But on the other hand, the dark the you cannot have some random curved space time, and because at least we have many very stringent test of the general relativity. We know that there is certain equation for specific equation we have to follow basically, and so what I'm saying is like the dark matter and the source the changing and space-time following the general relativity. That's the kind of experimentally tested way. Putting this way, but indeed, you can almost can think about it like a. Well, yeah, you can say, oh, I don't have a dark matter. I can replace dark matter by the dark matter effect on the space-time change, right? So that's excellent
Okay,
question.
yeah.
Yeah, yeah.
I see, I see. And my second question, it would be a follow-up question. Could the reason why star systems at the edge of galaxies not slowing down be attributed to maybe the amount of gravitational force that is accumulated throughout the galaxy? Meaning, could all the massive objects be interlocked in a specific way, similar to how the moon is interlocked with us, with the Earth specifically? And this is why everything is kind of dragging everything at the same speed.
Uh, um,
Because I mean, when we talk about gravity, we always talk about how gravity falls off the further we
Mm,
get from the center of the concentration of mass. But we're never really talking about the rest of the massive objects that exist in the galaxy contributing to magnifying the gravitational pull. So everything could be interlocked with each other, and they're simply dragging each other together, and the force is becoming stronger based on how much massive
mm,
objects there
mm,
are in us in
mm,
any
mm,
given
mm, mm,
galaxy
mm.
specifically.
Yeah, very, very good. So first of all, I think that everything you can think about everything is locked together in a sense. Then you just change the system, right? So in the solar system, or in the Earth, like a moon around the Earth, you can think about that is locked in system. And similarly, you can think about the stars. When we talk about those rotation curves, they are locked together with the galaxy. And so they're just moving around the galaxy. This is a gravitational bounded system, except that there are too many objects in the galaxy, right? And to answer your question, I'm saying that even the let me use a different way to think about it. Suppose the moon is moving around the Earth, right? Suppose for some reason the moon is moving around the Earth is faster than it should be. Okay, so
Yeah.
what it should be? The should be is like that the total mass of the Earth, right? So let's say that that, then you use the Newton law to know what is the predicted moon rotating velocity. But suppose you
Hmm.
observe that moon rotation velocity is higher than it should be, right? So then you probably also will infer there is some large amount of matter, at least some matter source gravitational force in between Earth and the Moon. So what I'm saying, those rotation curves has been basically established or to give us the evidence of dark matter in this way. Yeah, I don't know whether you now get a
I
better
see.
sense.
Yeah.
Yeah, the rotation curves. Yeah.
Perfect. Thank you very much. Thank you.
Okay. You're welcome.
Yeah, thank you. Kiko, did you want to?
Yeah, super cool talk. And I have this question that's been like itching at me for like a long time in regards to dark matter.
Mm,
So like, I think it was on the like after the dark quark slide, where it's something about like the possibility of dark matter having like energy states. So I was always curious about like, has anybody ever like investigated whether or not like because like if you have an energy state like when that energy state goes like down it has to release some form of something, and if it doesn't interact with light, I've always kind of wondered like what's the possibility of like the dark energy actually being the release of energy from like dark matter when it goes from higher to a lower energy state.
mm, mm. Yeah, very excellent question. Um, so how do I say this? So you do have so this is related to like a cooling effect. Since you want to have some high temperature state, you want to get a lower temperature state, you need to release some energy. And in the for the specific model I'm talking about, the dark QCD model, indeed there are other like dark hadrons. So dark hadron, sorry, let me talk about ordinary hadron. So there is an so ordinary matter, we're probably very familiar with the proton and neutron, right? Because that's ordinary matter. But there is another particle which is also hadron called a meson, which is pion. I don't know whether you heard this terminology before or not. Um,
Yeah, I've heard of mesons.
Okay, you had a meson, you have pion. So basically, those pions, mesons, they are lighter than baryon, proton and neutron. They are baryons. And similarly, in the dark QCD model, and there also could be darker meson, and those dark meson will be potentially the radiation help the system to be cooled down. So that will play a role as like when you radiate light and to cool down, and that will be radiate pion, those dark pion to cool down. So yes, indeed there are some other particles to help the system to get into lower energy state, for example. Yeah.
Awesome. Thank you.
You're welcome.
Yeah, thank you so much for those questions. Yeah, I have a few questions regarding more the exoplanets and how they basically would differ. I'm sorry if you maybe already explained it and I just didn't like. How would the this mass radius that you mentioned relation differ between this dark exoplanets and then regular exoplanets differ, and also other characteristics? um how do you think, like, would they be bigger, smaller, or would they be very similar in all these,
Right, right.
characteristics
Very, very
like
good, very good. So yes,
atmosphere?
I say yes. Yeah, 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 yeah. Atmosphere, I cannot answer. But if you look at page 27, so there is a band of the dark quark lattice just as example. So probably there are some other microscopic dark matter model. So here you do have some prediction uh, about the mass and the radius relation, and that depends on the specific dark matter model you will populate into that exoplanet mass and the radius um, uh, plot, right? But in general, the density could be, we don't know, because we have not fully understand the dark matter uh, particle property yet, so we don't know. And but it could be, I think could work in either way. In a sense, those dark matter state, they could be more denser than the ordinary matter. The ordinary matter, for example, they could be as dense as a neutron star and like a nuclear matter. And so they will populate on the page 30 will be the right lower corner. And they are very, very dense, extremely dense, if their density is like nuclear density or neutron star density, and they will have for fixed mass, they will have a tiny radius. And so, and obviously, um, we at the current moment, our telescope or sensitivity to the exoplanet measurement is a little bit only sensitive to like Earth radius, Earth mass, or Jupiter mass range. You see what I mean? Like we have not yet be so sensitive to some like a very heavy and also very small radius yet. And but the dark matter states could potentially populate in the right lower corner, and as well as the left upper corner. And but then you ask me what is the specific prediction for the dark states. I cannot answer that question because I don't have any other measured data to, even though if it's a dark QCD, I cannot fix what is the generic scale in the dark QCD yet at this moment. And but that situation maybe will be changed in I don't know how many years later if we discover the particle property of dark matter, and then we will know more detail and how those objects are formed. Uh, yeah.
Yeah, thank you. And do you have predictions on where, maybe, for example, in the galaxy or even solar system, what type of solar systems regions would be more likely to have like dark exoplanets, or do you think it's just as distributed like the exoplanets we can see and
Mm,
measure?
mm, mm, mm. Okay, very, very, very good. So, to answer, I think in general, the most like one possibility is like the dark exoplanet. They are floating, which means they are not bounded by any any star, any ordinary star. Uh, so that one, if that is the case, then you just use the microlensing method to detect. And even for ordinary exoplanet, people also are looking for this kind of free floating exoplanet using microlensing method. So that is one possibility. Another possibility is when people trying to understand the large scale structure, which is like understand the galaxy formation, star formation, and for example, star formation, especially there are some other what they call the top three stars, which is the earliest star, but we don't have the current observation of the that type of star. But for some earlier from the stars, for example, because the star formation, you can think about there is a bunch of gas cloud. They are become heavy and heavy, so they are gravitational collapse to form stars. And during that process, they also have a gravitation. They provide a gravitational well, so they can also attract the dark matter. And as a result, some star formation period, they maybe can attract some dark objects around that. And as a result, after they form stars, then the dark, let's say dark planets, they maybe will be bounded by that star system. So that is one possible ways for those dark exoplanet to be moving around a star. But at this moment, we don't have kind of detailed calculation to estimate what is the probability for this type of bounded binary system. For example, we probably that will require more study along this direction, and also in conjunction to star formation, for example. It's a little bit more involved physics calculation, for example. Yeah, yeah, I cannot provide an answer at this moment. Sorry.
Yeah, I believe. I just wanted to,
Mm.
the know what the theory is, because
Yeah,
we
yeah.
had actually a guest speaker here last week that talked about
Mm.
the theory about dark matter density spikes around
Right.
massive black holes. So that's why I thought maybe
Mm.
there's also a theory,
Mm.
to predict basically these type of exoplanets
Yeah,
or ways
I think there
to.
is some possibility, yes, but the detailed answer we people has not yet worked out yet. Yeah, to be worked out, I guess.
Yeah, that makes it so interesting, right? Because we don't know too much about it. And
Mm.
do you think, are there any future technology developments that you would wish or people are working for that will make the detection maybe um, better, easier, or a little bit less challenging? I don't know if you can say that, but
Mm, mm, mm.
is there
Yeah,
is
yeah.
there anything that's being worked on?
We do have a few ongoing exoplanets, uh, telescopes, and I think the current moment is this kind of JWST and James Webb's telescope, probably the and but also there are some other like Gaia and which like what I was saying that would be very good ways to search for some missing transit. Um, but somehow I don't know any other like order of magnitude improve. And for example, you order of magnitude you can detect something like even um like 1/10 of the Earth mass exoplanet, for example. So that one I'm not a I'm not a yeah I'm not aware of any big another big telescope to detect much lighter uh, dark or exoplanets. But on the other hand, I think currently there should be more data coming from the James Webb's Space Telescope, and so again that already the spectroscopy information for some exoplanets that already can tell us a lot. So probably for the near future, that's already pretty good thing to work on. Yeah.
Yeah, it will probably generate a lot of data. How do you and your colleagues like go through all this data that's probably generated? Are you going to use like AI tools and things like that to help with the processing of all the data, or is it still something that is too specific and not enough data available to train systems like this?
Yeah, very very good. So I think at the current moment I don't have the plan to do that because I'm not an expert on machine learning. On the other hand, I have one new graduate student, and he is very into machine learning for physics, and so he's having starts to have some. So I start to learn some machine learning techniques, and but probably I need at some point to know the capability of the machine learning tool, AI tools, to say they can be applied to analyzing those like a few thousand exoplanet data, right? So, but I'm very interested to see that if that can be done, that would be very interesting. In some yeah, but to me, yeah, from the example, two exoplanets we worked on, yeah, we do think that definitely you need some non-trivial machine learning tools to help for this specific search, and yeah.
Yeah, I believe that it's a very specific, data that needs to be trained, and probably in the beginning will be a lot of work. Later on, then
Mm.
I don't know. Does it make sense? Because and will the theory maybe still a lot of factors or theory parts
I
change,
see.
so you
Yes,
would
yes.
need to keep training it differently, so it wouldn't make too much sense in the beginning,
Yeah,
maybe.
I have not. Yes, I see. Me. Yeah, I have not put too much thoughts. But indeed, there are some model parameters because when you, especially for light curve, how the orbiting, even you describe orbiting, is already like a few parameters to describe the inclination angle and how circular of the orbiting, and also those stars they have their intrinsic property. So, in instance, there is this so-called limb darkening effect, and so then you also need to model that. So probably you have order 10 parameters to model the system, and then you want to search for the light curve difference for one hypothesis, another hypothesis. Then you need to probably also minimize in terms of those 10 parameter 10 parameters space. And then you also want to do that for a few thousand exoplanet light curves. And each light curve, you probably have a few hundred points. But on top of that, there is another thing is when people talk about those light curves, so that's many, many cycles, many, many circle orbiting orbits. And you also need to find some clever way to fold those many orbits together into this kind of one cycle light curve. Even that one, I think only recently I saw, maybe in the last 2 years, I saw in the literature, people start to use some machine learning tools to do that folding of orbits of light curves. So because of that, I would guess probably, yeah, maybe it's yeah, maybe in the next few years, maybe this can be done. Yeah. Yeah.
Yeah, interesting. I'm really looking forward to the future, and I wanted to check with you because we've been going for an hour and a half. You're probably getting tired of speaking. Um, and yeah, I wanted to make sure that we don't take more like too much time of your day. So um, yeah, thank you so much for explaining your work, and also the principles behind it so well, and for answering so many questions. This was a really interesting talk and discussion, and I'm really looking forward to the future because there are so many unknowns, and um, it's really exciting because so many everyday things we
Yes.
know a lot about, and
Yeah. Yeah.
yeah, that's a true new frontier. So thank you for sharing that with us, and yeah, we wish you all the best for the future, and we are curious to follow your research. Thank you so much.
Thank you for the invitation. Yeah, nice to chat with you guys. Okay.
Yeah, thank
Bye.
you. And thanks
It
everyone.
was an honor, doctor. Thank you very much.
Yeah, yeah. You're welcome.
Yeah, thanks for all the questions. And yeah, I hope to hear you all soon, and maybe also we get to invite you back maybe next year or so. So yeah, all the best, and thank you everyone wherever you are. Enjoy the rest of your day, morning, evening, and I'm closing the room in three,
Take
two,
care.
one. Bye
Thank you.
everyone. Thank you.